Now we're gonna look into the smallest deployable units of computing that you can create and manage in Kubernetes is a pod. This is very important unit of Kubernetes. A pod. A pod is a group of one or more containers with shared storage and network resources and a specification of how to run the containers. A pod's contents are always co-located and co-scheduled and run in a shared context. A pod models an application-specific logical host. It contains one or more application containers which are relatively tightly coupled. In non-cloud contexts, applications executed on the same physical or virtual machines are analogous to cloud applications. So analogs to cloud applications executed on the same logical host, as well as application containers. A pod can contain init containers that run during pod startup. You can also inject ephemeral containers for debugging if your cluster offers this. So then the question arises, what actually is a pod? The shared context of a pod is a set of Linux namespaces, C groups, and potentially other facets of isolation. The same things that isolate a container. So within a pod's context, the individual applications may have further sub-isolations applied. A pod is similar to a set of containers with a shared namespaces and shared file system volumes. So while Kubernetes supports more container runtimes than just Docker, however, Docker is the most commonly known runtime and it helps to describe pods using some terminology from Docker. So now how to run a pod? That's the question. How to run a pod? Uh, we have run a one pod. So I'll show that. Sudo option I think the namespace that we have used, that we have cleared off. I think kubectl get pod. Yeah, no resources found in default namespace because that we have removed. So now we are going to create a new pod, but before that let's get into the concept. How can we create a pod? There are two ways. One is imperative, second one is definition file. So the following is an example of a pod which consists of a container running the image nginx 1.14.2. You see that? So this contains four sections. This is called a definition file. This is called a definition file. So this contains four sections. First one is API version. Then what kind of uh, object it is. It's a pod. Then in metadata, the name we have given is nginx. Then spec containers. Inside the spec, we have mentioned the container runtime engine should come into the action. Then the name of the container is nginx. and image name is going to pull nginx 1.14.2 and ports should be container port 80. Let's do this first and then we will move for the next concept. Okay, let's do this first. And first we will write a definition file for this. Okay, but before that let me do it in yeah, first pod.ml. Okay, so let's write our first definition file for pod. So the first one, as usual, the first section of this, the first object of this ML file is this definition file is API version. It's v1. Then as usual, what type it is, kind, I will go with pod because we are dealing with pod. So once you give the pod, you will get the information, a definition, sample definition file of pod. So let me take that. So now we have to attach a metadata section. Metadata is nothing but a data about the pod. Okay. So in this, the name I'm gonna give is first pod. Labels, I don't want labels at this moment. I will remove the labels. Then spec containers. So name of the container, I'll give nginx. Then image. So image, I'll get it from my account. Let me get back to the repositories, and here you should find SCADA nginx. I have to find nginx. Yeah, here nginx. We have how many versions? Only one. So let me copy this, paste it here. So the name of the image is this. Okay, then now resources I don't want at this moment. Let me remove this, and we have ports, and container port is, I want to map it with 80. I think rest all fine. I think no problem. So it's okay. Containers is fine. Name, image, ports. So total major sections are API version, and then kind, metadata, and spec. So now let me save this, and let me copy this. So here I'm gonna create a directory mkdir defs ls cd defs and mkdir. Okay, mkdir first pod cd first pod, and inside I'm gonna write first pod.ml. So here I'm gonna paste. So this is our first definition file. I'll save it. I think everything is fine. And now, so it's done. Now let's get back to our slide. So the definition file with 4 sections has been written, but in spite of nginx 1.14.2, I have gone with the nginx v1 from my account, my Docker Hub account. So then it's time to create a pod using kubectl apply option F. Okay, let's do that. Let's create that. So kubectl, apply, option F. So first pod ml. That's it. The pod, basically the first pod has been created. The name of the pod is first pod, and let me check. Kubectl get pod. Here it is. First pod running. It's up and running. So the container is up and running. So you can check get, sorry, kubectl get ns and default get so our first pod is up and running. So now let's get back to the slide. Okay, that's what the pod, and that's how we write a definition file, and that's how we create our first pod. Now we have a workload resources for managing pods. Usually you don't need to create pods directly, even singleton pods. Instead, create them using workload resources such as deployment or job. If your pods need to track state, consider the stateful set a resource. Pods in Kubernetes cluster are used mainly in two types, mainly in two ways. So pods in Kubernetes are used in two main ways. One is pods that run a container, the one container per pod. Pods that run a single container is the first way. So this pod takes one container. That's it. So one container per model is the most common Kubernetes use case. In this case, you can think of a pod as a wrapper around a single container. So Kubernetes manage pods rather than managing the containers directly. Then the second way is pods that run multiple containers that need to work together. So a pod can encapsulate an application composed of multiple co-located containers that are tightly coupled and need to share resources. These co-located containers form a single cohesive unit of service. For example, one container serving data stored in a shared volume to the public, while a separate sidecar container refreshes or updates those files. The pod wraps these containers, storage resources, and an ephemeral network identity together as a single unit. So each pod is meant to run a single instance of a given application. If you want to scale your application horizontally scaling your application horizontally means to provide more overall resources by running more instances. So you should use multiple pods, one for each instance. In Kubernetes, this is typically referred to as replication. Replicated pods are usually created and managed as a group by a workload resource and its controller. So then let's see how to manage these pods, how these pods manage multiple containers. the pods that we have seen so far can manage multiple containers, but how do they do that? So pods are designed to support multiple cooperating processes. Processes in this, obviously, as we have discussed in Docker image, a Docker image is a heavyweight one which consists of all the files, all the data. Sorry. Whereas a container is a just process which is running, which is a container is a process which is running from the image that we have built. So that's why I say pods are designed to run multiple cooperating processes. Processes means a container that form a cohesive unit of service. And the containers in a pod are automatically co-located and co-scheduled on the same physical or virtual machine in the cluster. So the containers can share resources and dependencies, communicate with one another, and coordinate when and how they are terminated. So let's take one example. So a container that acts as a web server. So this is our web server. A consumer fetches data from this web server. A consumer sends a request and gets a response from this web server. Then we will have a pod. This is a pod. We will have a one more container inside the pod, which is for a shared volume. This container is for files, to store files in a shared volume. Then we will have a separate sidecar container that updates those files from a remote source, as in the following diagram that you see on your screen. Now, some pods have init containers as well as app containers. So init containers run and complete before the app containers are started. If you look into this example, so we have a web server, and web server should be connected with a volumes container so that the volume container can store all the respective data and provide that data to the web server. And whereas we have a file puller, so file puller is our content manager. So now a file puller is like a sidecar. So now a sidecar container, this updates those files from a remote source as in the following diagram. So the sidecar updates the files into the volume, and then once the volume has enough files and some consumer, if he requests for certain files, then web server asks the volumes to respond with that file. Then the file will be given to the web server, and inside that web server it will be visible for a consumer. So here total 3 containers are running, and they'll be running in coordination with each other so that they can serve the consumer. That's the output. This is how a pods manage multiple containers. However, web server is the main container, volume is the shared volume container, whereas file puller is the sidecar container, and sometimes you can have an init container too. So pods natively provide two kinds of shared resources for their constituent containers, that is networking and storage. So then let's look into various pods and controllers. So now let's look into the pods and controllers. You can use workload resources to create and manage multiple pods for you. A controller for the resource handles replication and rollout and automatic healing in case of pod failure. For example, If a node fails, a controller notices that pods on that node have stopped working and creates a replacement pod. The scheduler places the replacement pod onto a healthy node. So here are some examples of workload resources that manage one or more pods. The first one is deployment, second one is stateful set, and third one is daemon set. So let's look into the pod templates. So controllers, we'll begin with the controllers. Controllers for workload resource create pods from a pod template and manage those pods on your behalf. So pod templates are specifications for creating pods and are included in workload resources such as deployment, jobs, daemon sets. Each controller for workload resources use the pod template inside the workload object to make actual pods. So the pod template is part of the desired state of whatever workload resource you use to run your app. So let's see the sample. Let's see some of the samples of uh, these definition files. So this is the first one. This is a job type object. You have an API version. For this, we have to use API version batch v1 and kind is job metadata. Name of this job is hello. Spec template. This is the pod template. Spec again container name. So basically busybox 1.28 we are bringing, and command, this is what we are executing, and it will come and say hello Kubernetes and sleep again. Restart policy on failure. So that's the pod templates ends here. Okay, this is one. This is a job type. So let's build. Let's create a definition file for this. So let me get into the VS Code and type job.yaml definition file. So API version. So I'll go with the batch v1. So then kind. This is job. Yes, we got it. So let me remove the top one because we got that. Yeah. So API version batch metadata name first job then spec it's not required, so let me remove this. I'll go with the template, and inside the template I'm gonna attach a command if it's required. This is the pod template. This is the pod template. Then spec, it's a container, so I'm gonna use a pi, or here I'll say array. Then image, I'm gonna take busybox 1.28 command. In spite of Perl, I'll say sh shell as an command, and after that option C. Then echo, what I want to echo is echo Hare Krishna Kubernetes and sleep 3006. Okay. Okay. Restart policy on failure. On failure, rest all it's fine. Or else I'll remove this. It's not required and sleep 3600. Yeah, this would be better. It's all fine. So let me save this. Copy this and get into and sudo option I, clear the screen, ls cd defs ls mkdir job def and cd job def vim. This is job def dot ml and paste it here. Okay, so that's it. Let me save this and quit it and say kubectl apply option F jobdef.ml. So the jobdef is invalid, spec template containers name invalid, array lowercase. Okay, got it. That's the mistake. It is absolutely wrong. So we missed it. Spec. The problem is with spec. Yeah. That's it. The job.batch first job has been created. And here is that. This is our first pod and this is our second pod. So it's been executed and the status is completed. It's not running because it has to come. It has to start and print a message and die. That's what it's gonna do. Clear? Yeah, that's what a job. And the following is an example of deployment. It creates a replica set to bring up 3 Nginx pods. Let's see that. So deployment, and this is a deployment object, and this is going to bring 3 replicas, basically 3 replicas of that. All are of Nginx. Let's quickly do this. def.ml API or kind. Yes, we got it. And let me remove this. It's not no more. It's not required. API version, fantastic, kind, deployment, metadata, name. I'm gonna go with Nginx deployment. Nginx deployment. Then specs selector is not required. Match labels, replicas, we'll put the replicas before that. Yeah, replicas, how many? 3. That's it. Rest all selector match labels. I'm gonna with Nginx only. Then template metadata labels app. I'll say Nginx. Then spec containers. I'm gonna push my Nginx image. That is, I'll get into that. Yeah, is this the one? Yes, this. Let me copy this and paste it here. Let me, yeah, fine. Resources is not required at this moment. I will remove this. And image ports container port 80. That's it. Rest all absolutely fine. Let's save this, copy it, get into our machine, cd mkdir, and after the mkdir, let me give the name of the directory here. I would say this is dep def cd def and enter vim def.ml and paste it. That's it. It's time to run kubectl, apply, option F, def.ml. So deployment.apps, it's not just pod, deployment.apps has been done. So the name is nginx dep. So created, let me see that. kubectl get pod. Here are the 3, all are up and running. You see that? The magic of the deployment object, you see that? All 3 are up and running. Then we can describe a daemon set in YAML file. For example, the daemon set YAML file below describes a daemon set that runs the flaunted Elasticsearch Docker image. So this we're going to do in our further slides, but for now you have seen 2 types. One is job type, second one is deployment type, and last one is daemon set type. So next we will look into the storage building blocks. So before that we will also see service here, and a service uses a selector to define a logical group of pods and define a policy to access such logical groups. Because pods are not durable, the actual pods that are running may change. A client that uses one or more containers within a pod should not need to be aware of which specific pod it works with, especially if there are several pods or replicas. So there are several types of services in Kubernetes, including cluster IP, node port, load balancer. A cluster IP service exposes pods to connections from inside the cluster, whereas a node port service exposes pods to external traffic by forwarding traffic from a port on each node of the cluster to the container port, whereas a load balancer service also exposes pods to external traffic as node port service does. However, it also provides a load balancer. So then we will look into the volumes. Volume, a container file system is ephemeral. If a container crashes, the changes to its file system are lost. So volume is defined at the pod level and is used to preserve data across container crashes. So volume can be also used to share data between containers in a pod. A volume has the same life cycle as the pod that encloses it. When a pod is deleted, the volume is deleted as well. So Kubernetes support different volume types which are implemented as plugins. So basically there are two types. One is persistent volume and second one is a persistent volume claim. So all these things, this service, volume, deployment, all these objects, we are going to look into these objects in deep. Okay, in our further forthcoming slides. For now, we will seriously jump into the pods. So let's get into our COPS machine. Now let me say kubectl get nodes, and here you can see three nodes are up and running at this moment. One is control plane and second one is remaining two are working nodes. So now to fetch the information about the specific node, we are talking about nodes, not the pods. To fetch the information about the specific node, say for example a working node, so we have to give kubectl describe and then node name is this. I'm going to give this, and let's say that's it. You got the lot of information, huh? Fantastic. Yeah, it's too much information. Let's go through it one by one. Let's scroll up a bit, reach command stage. Yeah, we got that. So here where we have described, this is a working node. You can see that name of the node, and then what is the role is node. It's a working node and it has a lot of labels, and US West 2A, you can see that that's one of the label, and topology annotations, timestamp, and here you can find out some more information. That's memory pressure, disk pressure, PID pressure, and addresses. You can find addresses, internal IP. This is what the internal IP of the node. This is external IP of the node. This is a private and this is public. And internal DNS. See this one, domain naming system, and then host name. Basically, the complete host name is this. Either you can use till here, and or else you can use complete host name to fetch or to get the information about that node. And external DNS, if you want to attach it using external DNS. So this is what the address of this one. So capacity 2 CPU and ports 110 it can take, maximum ports it can take 110, and memory is also given in kilobytes. And ephemeral storage, let me scroll up, I completely came down. Yeah, so machine ID, system UID, boot ID, kernel version also you got it, and then OS image that we have used is Ubuntu, you can see that, and operating system is Linux, architecture AMD 64, and kubelet version is v1.2 and kube proxy. So that's the lot of information you can find out from here. In addition to that, you can find out some of the CPU limits, memory requests, and CPU requests. And if I scroll down completely, CPU and memory, you can find out. Events, at this moment, there are no events, none events. Okay. So now this is pretty complex to understand, so pretty complicated to understand. So that's why what I'm going to do is I'm going to fetch the similar information in AML format. Let's do that. So let me go up, use the same command, attach option wo, and say AML. Okay. kubectl describe node and option wo ML. I think this option has been deprecated. That's okay, but that's how you basically convert this into the ML format. So then let's create a pod which basically runs an application. That's a Wipro app. So let me clear that, and meanwhile you can find out the way to do this. Okay. Now for that, I'll get back ls. So I'm in defs. So here I'm gonna create a directory which says the name of that is mkdir wipro wiprod wiprod. So wipropod, that's what. And cd wipropod, and inside no file. So now I'm going to create a file, vim wipropod.ml. So let me keep it. In spite of typing here, I'm gonna do the same here. So I'll create wipropod.ml. As usual, kind. This is a pod. Yeah, I got it. I got the pod. So kind. Now let me remove this first. Yeah, everything is fine. API version v1 kind pod metadata name I'm gonna give is Wipro app, and labels is an I'll give Wipro app again. Yeah, spec a container name is app container, and image I'll take from my organization, my Docker Hub organization. So let me click on here and click on repositories, and I would see I'll find vprofile Charan. This is what I want. So let me click on this and take the see all tag and copy this and put it here. Yeah, it's all fine. Yeah, yes, it's done. So now resources is not required at this moment. So I'll remove this. Okay. Then we have ports. So port, I will attach the name for the port. So it's a name Wipro app port, and the container port, I'll remove this. Yeah, that's fine. And the port I'm gonna give this time 8080. I hope everything is fine, no issue at all, no red mark. Let me save this, let me copy this, and let me paste it here. That's okay. Get back to VS Code, copy everything and paste everything. That's it. Save to WQ. Now it's time to run or create our pod. So for that, kubectl create F option and wipro wipropod.ml. Execute. That's it. Wipro app has been created. So now let's see what's the status of the pod. So kubectl get pod. Here it is, Wipro app. It's successfully up and running. You see that? One is ready and one is running. Now it's running. It's up and running. It's not dead. It's up and running. You can see that. Now let's just describe the Wipro app and we'll see. Just see the what's happening inside and what's the content is there. How exactly looks like this pod. Okay. We will look into the pod. We have seen it. We have gone into the container. We have gone into the image. Now we are going to enter inside the pod. So kubectl describe pod and the name of the pod is Wipro app. Wipro app. Yeah, Wipro app. Correct? Yeah. So this is our pod Wipro app. Let me scroll up and let's look into this one more time. The most important information for us here is required the IP. We'll begin from top. Namespace is default. You see that we have discussed in namespace. If you do not specifically attach a namespace while creating your pod, it will take a default namespace. This is the default namespace and Wipro app. Priority. So node, it's been created in this node. Okay, let me check. Which node is that? Copy this. Put it in sticky note. This is nodes object and let me paste it here. Now let's get into our instances and bring up node 463. Here it is, the bottom one. This is in this node basically. Node, it is in US West 2B. So in working node, in this node, it has deployed that pod. So I'll show you this one more time. I'll take you back to our picture and I'll show it to you so that it will be much clearer. Yeah, here it is, the diagram. Now I'll show you that. So what we are experiencing at this moment is a pod in working node. A pod in a working node. I'll show you in both places. Here you can see that. So this is our pod which is in this node. And inside that inside that pod, this is your container. This app container is running. You can see that all practically you can see. And inside that container, this container is spun from this image docker.io vprofile charan. Okay, from my image. See, vprofile charan, vprofile v1 tag. Now here it's everything is clear. I'm going to show you one more time. This is the working node. Inside the working node, you have a Docker and you have a pod. Inside the pod, you have a container. I'll show you that exactly. First, I will show the working node. This is our working node, which is just an EC2 instance. Now, inside this EC2 instance, you have inside this node, that's our node EC2 instance. Inside that, you have a container. The IP of the container IP is that. And inside that container, this container consists of this container is spun from this image and image ID and the port 8080. This has been exposed. The app has been exposed to the 8080 and then host port not yet mapped 0 and state is running. That's how it works. You see that? A node, a pod, a container. Everything you should be able to see here. I hope it's brilliant for you too. Then you have a mounts var run secret kubernetes dot. These are mounts attached and conditions. Then volumes, a kube API access and more information downward API and events. This is what the final one, events. As our pod is up and running, so these are the events. So the normal scheduled, okay, it's been scheduled. The first it has started with this one 76 seconds when you said create a pod. That time first the scheduler has come into the picture. Let me show you that. Let me show you that. Don't worry, everything I will show you. This is our scheduler. Okay, the scheduler first came into the action 76 seconds ago. It has came into the action. That's default scheduler. And what it has done, successfully assigned default Wipro. Just a minute. Yeah, it successfully assigned default VPR. Okay, the scheduler. Then after that, we have pulling. The next event is pulling. For that, the kubelet has come into the picture, because where will be the kubelet? Kubelet will be inside the working node. So here the kubelet, the scheduler, through API, it has communicated with the kubelet, and then kubelet is in, the kubelet has swung into action. Now the kubelet has started pulling the image. The kubelet started pulling the image. That is successfully, then kubelet successfully pulled the image. That's a v profile charan v profile app v1. That's been done. So then created, who has done? Again kubelet. Started, who has done? Again kubelet, because it all happening inside the node, a working node. Whereas the first one, the scheduler, has took the initiative from the master node or control plane. Remaining all activities are done by the kubelet. That's what this image conveys. Your scheduler through API server communicate to the kubelet. That's it. Your work is over. Then the kubelet swings into the action, and remaining all activities will be done the kubelet using the containered or container engine, a runtime container engine. Now let's get back to the action now. That's enough. Too much explanation. So that's how Wipro. So that's how the pods will be used, and that's how we create a pod, and that's how we describe the pod. So let's meet in another object.